Okay, so in our last couple of videos, we've had a look at critical points and what they are and how we can find them. And we've had a look at the sign test and how we can use that to determine what type of critical point it is that we found. And we're going to extend on this idea a little bit further now into what we call the second derivative test. Okay, so I've got a couple of graphs here, and in the red we just have a function of x. Okay, and in the blue, it doesn't really matter what that function of x is. And in the blue, we have the derivative for that function. Okay, and we're gonna compare the relationship between these two curves. So if we start off with the axes and what these curves actually represent, here we just have f of x and x. Okay, so for every x value, we're getting a y value. But on the blue curve, what this is representing, okay, is we've got our x-axis, but for every x value, we're getting an output value that represents what the gradient is at that particular point for the red function. So any time that this blue curve ventures above the x-axis, or when y is positive, we're saying that the red curve then at that point has a positive gradient. And down here, when it ventures below the x-axis, okay, or into when y is equal to 0, we're saying that the red curve has a negative gradient. So we're going to explore these curves a little bit further. I'm just going to get rid of that label there to give us a little bit more room now that we understand what this blue function is actually representing. So if we start off on the red curve by looking at the critical points. So for the red curve, there's a critical point about here, and there's a maximum here, and another minimum just about here. And let's see where they line up on our blue curve. So to start off with here, when x is negative 0.5 something, or whatever it is, seeing where that is when the blue line is negative 0.5 something, so about there. And the same goes for this point. So it looks like when x is 0. And for this one here. Okay, and these lines, these points all line up directly like that, and they all line up on the x-axis. So why do they all line up on that x-axis so nicely? Well, it's because at our critical points in orange on our red curve, we know that that is when the gradient is equal to 0. Okay, so on the blue curve, it is saying that all of these points in orange here and here and here all have a derivative or a y value equal to 0. Okay, so that's when y is equal to 0. So that's telling us that the gradient at that point for the red curve is going to be 0. And we know that because it is a critical point. Okay, and let's have a look now on our red curve at what we call not horizontal points of inflection or stationary points of inflection. They're the ones that actually get a derivative or a gradient equal to 0. Okay, so that point there would be a horizontal point of inflection. We're looking at what we call just points of inflection. So on our red curve, some points of inflection. So that is when the gradient starts to become less steep and starts sort of plateauing out. So see here how this gradient is coming up and up and up. And about here, it starts to sort of plateau out. Okay, that point there is what we call a point of inflection. So let's see if we can find another one. It's going to be between two turning points, okay? So it's sort of coming back up, ready to come back down again. So here, it's coming back down, but it needs to start getting ready to go back up again, okay, at this turning point. So there's a nice point of inflection about here. It's coming down, and then it starts plateauing out, getting ready to go back up. So those points there in black, and I'll just get rid of these arrows because we need this space. Those points there in black are points of inflection, where the gradient stops being so negative or positive and it starts changing and plateauing out, ready to go the other way. And if we look at if I put these in blue, and we look at where these line up on our blue function, come down here like this, they're actually the turning points of our derivative function, right? So that's interesting. So we see on our blue function, these are actually the turning points of this particular function. And that is because that is when the gradient is starting to change, starting to, here for example, yes, the gradient is still positive the whole way up to this turning point, okay? However, it's positive up to here where it's still positive, but it starts becoming less positive, right? So it's still positive, climbing steeply, and then it gets to this blue point where it's still positive, so it's still in this positive region, but it starts becoming less positive, ready to duck into the negative gradient region down here. Okay, so we are able to use the gradient of this red line to be able to map out our blue line. So if we do that for the whole way, okay, so if we start off, and I'll do our over sketch in purple. So if we start off at this point, okay, so we're starting off down here on the blue curve. We have a negative gradient all the way down to this critical point here where the gradient is going to change. So it's a negative gradient, so we need to stay in this negative region, okay, all the way to our critical point. But it's then going to start being positive. So we need to move in an upwards direction whilst we're still staying in the negative region up to that critical point where we can then start going positively through here. We're going to get to this blue point, which is our inflection point, and that's going to be the turning point on our blue curve. Because, as we spoke about earlier, yes, we're going to stay in this positive region, so the gradient's still positive up to this point here, okay? But it needs to then start changing to move closer to the negative region so that as we duck over this side, it's going to become negative. And it's going to do that again all the way down here. All of this space here, it's all negative gradient, but it's going to change here. It's going to start becoming less negative. So it's still negative, okay, but at this point here, sort of down here like this, it's going to start becoming less negative. So it starts becoming less negative through here, ready to come back up the other side, positive gradient. And we start coming back up the other side here, get to there where we can come up here and start with a positive gradient. Okay, so it's a little bit tricky to get your head around, but once you think it through, it is actually doable. And now I'm going to erase all of these markings because we're now going to look at what we call the second derivative. So that's just the first derivative, okay? That's going from the red function there to the green function, okay? And now we have this green function down here. This is the second derivative of x. So this is the double derivative of x, okay? Also, just a little side note with a different notation that we have. If this was y is some function of x or whatever, y is something of x, then this would be dy over dx. The second derivative would be d squared y over dx squared, okay? And then for the nth derivative, it is dny over dx to the n. So for the seventh derivative, it would be d7y over dx to the 7. Okay, so the different types of notation we have there, but we'll stick with this for now because it is, it's the most simple way of writing it. So we'll get that out of the way. You might see that notation in your textbook. So now we're going to compare the all three of these functions. So we're going to compare the original function to its derivative to its double derivative. Okay, and I can't really zoom in too far, okay, but we'll go from there. And if we line up, we'll start with the critical points again in orange on the red curve. So it was about here, here, and here. Because these are the critical points. They're the ones that we're interested in, okay? We're coming up with a new method to find what type of critical point it is that we found. So for example, you've done the algebra and you've worked out, okay, that point there in orange is a critical point, but I want to know what type of critical point it is. And we're going to determine that by mapping out the second derivative, and that will tell us. So if we line this up, remember that it will come down here to when, should come there, to when the gradient is 0. If we follow that all the way down, we're going to come to here where if this graph extended out, like kept going all the way out, it would be in this positive space, right? So for a minimum, for this is a minimum here, this critical point, the double derivative or the second derivative is going to have a positive value at that point. If we check that for the other minimum over here and we come down to there and all the way down this side, if this picture was big enough, it would come sort of all the way out here, right, over time, and we would be in this positive space. But what about this critical point up here, this maximum? Well, this maximum, we come down this x-axis here, and this one we can actually see. Here we are in the negative space of our second derivative. So there we're in the negative space. So that is going to be a maximum. So a minimum up here, we know means in our first derivative, it means a x-axis intercept. So when y is 0. And down here, it means we are in the positive y-axis. So we're up in this positive space up here. Okay, so we're up in here for a minimum. And for a maximum, it's still a critical point. So in our first derivative, we are at the x-intercept, or when y is equal to 0. And for the second derivative, we are in the negative space, or the negative y-axis space. Okay, so down here in this negative space below our x-axis. So if we had our critical point was critical point when x equals 0, okay, then and it was a maximum, which it is in our case. So when x is 0, or when x appears to be 0, we have a maximum. And we're going to say then f of 0 is equal to whatever f of 0 is equal to. Okay, so something. But the derivative is going to be equal to 0, right? Because we know at that point the gradient has to be equal to 0. So the derivative is equal to 0. And the second derivative has to be in the negative space. So the second derivative has to be negative, or it has to be less than 0, right? And the same goes for a minimum, but for a minimum, if we had a minimum at f of 0.9, okay, so say around here somewhere, okay, and that was a minimum, then again, the first derivative will be 0, because that's saying the gradient of the function at that point will be 0, because it's a critical point. That makes sense. And the second derivative, as we found out, will be positive. Okay, so it has to be in this positive space up here. So they're the key points to take away from this little section, is that if we have a maximum, then the first derivative is 0 and the second derivative has to be negative. If we have a minimum, then the first derivative is still 0, the gradient is still 0, right? But the second derivative is going to be positive. And then there's the last situation, which is what if we have a horizontal point of inflection? Okay, so if we come down here and we have a look at these graphs. So we have, again, in red, we have a function of x, or instead of f of x, because we've used f of x, I'll call this g of x. And in the blue, we have the derivative of g of x. And in the green, we have the double derivative of g of x. So for example, if we go into this red section here, and we compare the relationship between the red and the green, let's look at our critical points in red. We only have one, and it's a horizontal point of inflection, right? And if we see where that lines up on our blue curve, it should line up at 0, 0. Okay, it should line up when x is 0, when y is 0, because the gradient has to be 0. Okay, the gradient at any critical point has to be 0, so that makes sense. And if we just practice our drawing of the second derivative, because in a test you might get given this red curve and you're asked to draw a rough sketch for the function or for the graph of the derivative, so being able to draw this blue curve. Well, here we have a positive we have a positive gradient climbing up and up and up, but it's becoming less positive, okay, as we get to the critical point. And it's getting ready, not to go down in this time, but it's getting ready to go back up again. So here, we're in the positive section, and we're staying in the positive section, but we're moving closer to the negative section, ready to go sort of either way, ready to jump either up or down, depending what we have to do at the critical point. And in this case, we have to go up. Okay, so we end up with this parabola. And if we see where this horizontal point of inflection lines up, where this critical point lines up in our green function, in our double derivative, it also lines up when it's equal to 0. Okay, so up here we found out that for a maximum, the double derivative has to be less than 0. For a minimum, the double derivative at that point has to be positive or more than 0. For a horizontal point of inflection, the gradient is equal to 0, of course. Okay, so any point of any critical point, the gradient has to be 0, but the double derivative is also equal to 0, and we'll highlight this one in purple. So for a horizontal point of inflection, the gradient is 0, but the double derivative is what seems to be changing. Okay, so all of the gradients here at any critical point we know are equal to 0. So on that first curve, they're all going to be equal to 0. So we can't use that to tell us anything. But what is changing, and I'll use a different colored arrow, I'll use a blue arrow, what is changing is the double derivatives. And if the double derivative at your critical point is negative, then you're going to have a maximum in the yellow highlight there. If your double derivative at your critical point is positive, you're going to have a minimum in the blue highlight. And if your double derivative at that point is equal to 0, then you're going to have a horizontal point of inflection. Okay, so they're the key takeaways, but the reason I took you through sort of the painful process with the graphs is being able to understand sort of where it comes from, because you might be asked to be able to graph these in a test or something like that. Okay, but it's important to be able to sort of see the relationships and see it graphically, so for visual learners. Okay, so let's have a couple of examples. Let's say we have the function of x is equal to x to the power of 4 on 4 plus 2x cubed plus 4x squared. Okay, and we are asked to find the critical points, okay, and specify what type of critical points they are by using the second derivative test. So let's find the critical points. Well, we know that is when the derivative is equal to 0. But what is the derivative of this function? Well, it's going to be 4x to the power of 3 on top of 4 plus 6x squared plus 8x. And we can simplify this down by cancelling these 4's out. We get x cubed plus 6x squared plus 8x. And we want to know when that is equal to 0. So we have a common factor of x here. So let's bring a common factor of x out. So we end up with x squared plus 6x plus 8. And then we have some brackets here that we can factorize. So we end up with x plus 3, x plus 2. Okay? Oh no, x plus 4, x plus 2. Okay, and we want to know when that is equal to 0. Well, the x out the front, if we make that equal to 0, then we'll get 0. So x can be 0. And the null factor theorem, here we can say that x is minus 4 will do it. And in this bracket, if x is minus 2, that will also do it. So we have a few critical points here. Okay, so let's substitute x is 0 back into f of x. So we'll get the point 0, comma, and then if we work out what f of 0 is, so doing that, we get 0 to the power of 4 on 4 is 0, plus 2x cubed, 0, 4x squared, 0. So we get point 0, comma 0. And if we substitute the point minus 4 back in, okay, so we end up with minus 4 to the power of 4 on 4, and 2 lots of minus 4 cubed, and 4 lots of minus 4 squared. Okay, so let's do a little bit of a working out here. So 4 times 4 is, and I'm ignoring this negative sign because it's an even power, right? So 4 times 4 is 16, times 4 is 64, times 4, 60, is it 256? Let's check on a calculator. 64 times 4, yes, 256. We end up, but of course, 256, we're dividing by the 4 again, so we get 64. And then the negative 4 to the power of 3, well, that is going to be negative 64, times by 2 is a negative 128. So we're going to take 128 here. And we're going to add on, essentially, 4 cubed here. So, again, 64. So we end up with 0 as well. So we end up with a point negative 4, comma 0. And the last point is when x is equal to minus 2. So we get minus 2 to the power of 4 on top of 4. And 2 lots of minus 2 cubed, and 4 lots of minus 2 squared. So let's have a look. So we get minus 2 to the power of 4. 2 times 2 is 4, times 2 is 8, times 2 is 16. Divided by 4, we will get 4 here. And then minus 2 times minus 2 is 4, times minus 2 again, you're going to get minus 8, times 2 is minus 16. And then minus 2 squared gives us 4, times 4 will add 16. So these will cancel, and we're left with just the 4. So we get the point minus 2, comma, 4 there. So now we need to specify what type of critical points these are. And we do that by finding the second derivative. So if we know the first derivative, okay, which I'll highlight in blue, we know that this is our first derivative, or this part here. Once we'd simplified it down, let's take the derivative of that. So the second derivative of our original function is going to be the derivative of the first derivative, which is the derivative, or the change with respect to x, of x cubed plus 6x squared plus 8x. So if we find that, we're going to get 3x squared plus 12x plus 8. And now we're going to substitute these points, or when x is 0, when x is minus 4, and when x is minus 2, into this equation, so into our double derivative, and see if it's less than 0, equal to 0, or more than 0. So the double derivative when x is 0 is going to give us 8, and that is greater than 0, therefore we have a minimum. The double derivative of minus 4, well, minus 4 times minus 4 is 16, times 3 is 48, so we get 48, and then minus 4 times 12 is going to be take 48 plus 8. So we cancel those out, we're left with just 8, which is greater than 0 again, so we get a minimum. And the last one is when the double derivative is equal to minus 2. And what do we get here? Well, minus 2 times minus 2 is 4, times 3 is 12. And then minus 2 times 12 is negative 24, so we take 24 and we're adding 8. And that there is going to be less than 0. Okay, this is minus 12 plus 8 is minus 4. So we're less than 0, therefore we have a maximum. Okay, so we have a few points here. We can label that this point here is a minimum. This point here is also a minimum, but this point here is a maximum, as per the second derivative test. Okay, and we'll do one more little example, which is when we might get a horizontal point of inflection here, okay, if I've planned it out correctly. So let's say that we have a function f of x is equal to x to the power of 4 on top of 4, add 2x cubed and 4x squared, okay. Okay, so the final example that I want to do is, let's say that g of x is equal to 3x to the power of 3. Okay, well, we know that the derivative of this function, to find the critical points, is equal to 9x squared, and we want to know when that is equal to 0 to help us find our critical points. And this happens when x squared is equal to 0, or x is equal to 0. And if we put that back into our original equation, so g of 0, that's also equal to 0. 3 times 0 to the power of 3 is 0. So lots of zeros, but we get the critical point 0, 0. And if we use the second derivative test, so a super quick way, rather than doing like the sign test where we've got to, take small points and then plug it all into our calculator and do all of that sort of stuff, if we just take the double derivative here, which is going to be 18x, and we take the double derivative when x is equal to 0, 18 lots of 0, which is also 0, well then if it's equal to 0, okay, so we know that if the double derivative is equal to 0, then we have a horizontal point of inflection at that point. Okay, so remember, if it's less than 0, we have a maximum. If it's more than 0, we have a minimum. But if it's equal to 0 at that point, then we have a horizontal point of inflection. So at the point 0, 0 on this curve, we have a horizontal point of inflection. And if you're interested, there's the curve for this. I'll draw the curve in red. it actually just looks something like this, which makes perfect sense. If you go through the point 0, 0, you're going to get a horizontal point of inflection. Okay, thank you.